I'm Soumya, and in this video I'll be covering four main topics: Hermite polynomials, Lagrange polynomials, moment of inertia matrix, and rocket propulsion mechanics using Lagrangian and Hamiltonian equations. So now we will see Hermite polynomials. Hermite polynomials were first developed by Laplace and later worked on by Chebyshev to their current state. Hermite polynomials can be defined as a classical orthogonal polynomial sequence. By polynomial sequence, we mean that they are a sequence of polynomials as a solution, and by orthogonal, we mean that every two terms are orthogonal to each other. Meaning that if you integrate them over real space from minus infinity to infinity over a weighted function, then their value will be 0, and this we will see later as a property of Hermite polynomials. Hermite polynomials have several applications. So they arise in Edgeworth series, and those are known as probabilist Hermite polynomials. And they also arise as eigenstates in quantum harmonic oscillator, and those are known as physicists Hermite polynomials. First, let us see probabilist Hermite polynomials. We will represent the function as he of n of x, which is the nth polynomial in terms of x, which can be written as minus 1 to the power of n into e power x squared by 2, nth derivative of e power minus x squared by 2, which can also be written as x minus d by dx of whole to the power n. So now we come to physicists Hermite polynomials, which can be written as minus 1 power n into e power x square and nth derivative of e power minus x square, which is again written as 2x minus d by dx whole power n. These two are not exactly the same because they can be rescaled into each other. So if you want to rescale physicists into probabilists, we use this formula equal to 2 power minus n by 2 hn of x by root 2. And if you want to rescale probabilists to physicists, we use this. Now let's see first few polynomials in probabilists. So he of 0 of x is 1, he of 1 is x, and he of 2 is x square minus 1. For physicists, of 0 is again 1, of 1 is 2x, and of 2 is 4x minus 2. How we got this is by simply substituting n in the given equation here for both the series. And now we'll come to the properties of Hermite polynomials. Before that, we need to know that since these are a sequence of polynomials, they're basically the solution to a differential equation, a generalized differential equation. Here the equation is u double dash minus xu dash is equal to minus lambda u. Here u is our function of x and lambda is a constant. This is for probabilists, and for physicists we have u double dash minus 2x u dash is equal to minus 2 lambda u, where again u and lambda stand for the same thing, a function and a constant. Now the properties of Hermite polynomials. First one is orthogonality. As we previously mentioned, the sequence of polynomials are orthogonal. So if you integrate them from minus infinity to infinity and multiply two Hermite polynomials over a weighted function, then the value will be 0. This weighted function is e power minus x square by 2 for probabilists and e power minus x square for physicists. To simplify it, you can write it as root 2 pi n factorial into Dirac-Delts function mn. With Dirac-Delts function, as we know, it is 1 when m is not equal to n, and it's 0 when m is equal to n. Similarly, we can write physicists as root pi into 2 power n into n factorial into Dirac-Delts mn, where it's the same, it stands for the same thing. So that means from this property we know that every two polynomials in the sequence are orthogonal. Second, the Hermite polynomials are complete, which means they satisfy the following equation. So if you take a mod of the function and square it over a weighted function, then the integration from minus infinity to infinity will be less than infinity, so it's bounded basically. And here the inner product of the function fg will be given by f of x, g of x into w of x integrated over minus infinity to infinity. Finally, to get our Hermite polynomials as a sequence, we have certain recursive functions. So if you want n plus 1 of x, then you can write it in terms of n of x and n dash. So he n plus 1 of x is x hen of x minus hen of x whole derivative. And similarly, hn plus 1x is equal to x into hn of x minus hn of x derivative. So these are the recursive functions to generate the Hermite polynomials. One last topic will be the contour integral of these polynomials. So you can write them as integrated over a contour over the origin. So you can write problem list as n factorial by 2 pi I contour integral of e power tx minus t square by 2 whole divided by t power n plus 1. And for physicists, n factorial by 2 pi I contour integral of e power minus t square plus 2tz by t n plus 1. As we can see, the equations are very similar, but they differ basically in their constants, which will give us different values. But again, the power of the values and the degree of the equation will continue to remain the same. So this is Hermite polynomials. These polynomials were developed by Edmond Laguerre. Just like the previous set of polynomials, Hermite polynomials, these are also classical orthogonal polynomial sequences. In fact, Hermite polynomials and Laguerre are related to each other by these two equations. So here, this represents Hermite polynomials and this represents Laguerre. And using them, you can transform one set of polynomials to the other. This is used for the even polynomial and this for the odd. So Laguerre polynomial, since it's a polynomial sequence, it is the solution of a differential equation, and this is the differential equation: x y double dash plus 1 minus x y dash plus lambda y is equal to 0. Lambda is a real number and a constant here, and x and y are functions. So now there's also a general associated Laguerre differential equation, which is very similar to this, except there is also a constant called alpha here. So you have xy double dash plus alpha plus 1 minus xy dash plus lambda y equal to 0. And here lambda and alpha are real numbers and constants. So the solution for this can be seen through recursive functions where n plus 1 ln plus 1 x is equal to 2n plus 1 minus x ln of x plus minus n ln minus 1 of x. So from this, from one Laguerre polynomial, you can get the polynomials of higher order. But if you are using the generalized equation with alpha here, you have to make small modifications. So you will have plus alpha in this term. So it will be 2n plus 1 plus alpha minus x. And here n plus alpha into ln minus 1 of x. Now, substituting values of n, you will get some, let's see the first few polynomials. So L0 of x is 1, L1 of x is 1 minus x. If you're using alpha, then it will be 1 plus alpha minus x, and so on. L2 of x is half of x square minus 4x plus 2, and L3 of x is 1 by 6 into minus x cubed plus 9x square minus 18x plus 6. So the generalized equation for these polynomials can be seen as ln of x is equal to sigma from k is equal to 0 to n minus 1 power k by k factorial n into nck into x power k. And the Rodriguez representation is ln of x is equal to e power x by n factorial into the nth derivative of the product of x power n and e power minus x. There is also a contour integral for the Laguerre polynomials, just like Hermite, and that is equal to 1 by 2 pi I into contour integral of e power minus zt by 1 minus t whole divided by 1 minus z into t power n plus 1. We can see from the contour integral that this will enclose the origin, but not the point where z is equal to 1. Finally, as mentioned, these are orthogonal sequences. So integrating them over from 0 to infinity, f of x, g of x over a weighted function e power minus x will give you 0, which is their inner product. Finally, these polynomials have a lot of applications. One such application will be the use of such polynomials to solve Gaussian quadrature equations. Basically, equations of this form, where you integrate from 0 to infinity a function f of x into e power minus x dx. And to solve them, you can use the Laguerre set of polynomials. So now we'll start the topic moment of inertia matrix. So we know that the angular momentum of a system is defined as I omega, or mr cross omega cross r. So here let us consider a body with I particles. Then if each particle is located at a position vector of Ri with a mass mi, then the angular momentum of the entire system is sigma I to m MI-RI cross omega into Ri, where omega is the angular momentum with which the body is rotating. So Ri, of course, these are all vectors, so they will have three-dimensional components. So Ri will be xi, yi, zi, and omega is equal to omega z, omega y, omega z, omega x, omega y, omega z. Now, to calculate the angular momentum of the entire system, we'll go through a step-by-step process. First step, what you do is you calculate omega cross Ri. So if it's doing a cross product, let's say it is equal to Ia plus Jb plus Kc, where A, B, C are the respective cross product components as shown. So after this, after you calculate this step, next step will be crossing this with Ri. Ri cross omega cross Ri. So this, so when you know that Ri is xi, yi, zi, and you cross it with ABC, and these are your components. When you substitute all the calculated values and simplify the final matrix, you will get something like this. So you will have sigma mi yi square plus zi square sigma minus. You'll see that some terms have minus mi xi yi, mi xi zi, and so on. Once you simplify each of the matrix, you see that they're symmetrical and similar. It's a symmetric matrix. And what we have done is we have separated all these components from omega x, omega y, and omega z. So that crossing this with this will give you your initial angular momentum matrix that we are calculating. So finally we are able to write the angular momentum of the system in terms of I omega, where I is this matrix which we have just calculated. And in this matrix, Ixx, Iyy, and Izz are the diagonal elements, and these are known as the moments of inertia. And Iyx, Ixy, Ixz, and Iyz, these are the products of inertia. And also, since it's a symmetric matrix, Iyx will be equal to Ixy, Izx will be equal to Ixz, Iyz will be equal to Izy. And this is, of course, we are assuming I discrete particles. If you assume a continuous system and you integrate, then the formula will be transformed like this: integration of y square plus z square dl. And this concludes our moment of inertia matrix. Now we will study the mechanics of rocket propulsion using Lagrangian and Hamiltonian equations. Let us start with Lagrangian equation. We know that the kinetic energy of a system is given by half mv square, but first let us start with analyzing the system. So we are considering a rocket which is moving away from Earth. Let us take the height of the rocket, or the coordinates or position vector of the rocket, as q, and its derivative with respect to time as q dot. These are the generalized coordinate notations that we use. So now our kinetic energy will be half mv square or half mq dot square, and our potential energy is mgq or mgh, depending on whatever notation you use. The Lagrangian energy of a system is defined as kinetic energy minus potential energy, so k minus u. So it's half mq dot square minus mgq. We know that the equation to use for Lagrangian mechanics is d by dt of dou L by dou q dot minus dou L by dou q is equal to 0. So let us calculate the values and substitute. Now when you calculate dou L by dou q dot for this k minus u, you see that only this term depends on q dot, so you will get mq dot, because 2 and 2 will get cancelled. And when you calculate dou L by dou q, since only this term depends on q, you will get minus mg. Substituting these in the equation above, you will get d by dt of mq dot plus mg is equal to 0, dou by dt. So then, since m and q dot both depend on time, so using the multiplication property of derivatives, you will first write m q double dot plus dou m by dou t q dot is equal to minus mg. And this is our equation of motion using Lagrangian. Now let us use the Hamiltonian approach. The Hamiltonian energy of a system is kinetic energy plus potential energy. So the Hamiltonian is calculated as half mq dot square plus mgq. The Hamiltonian equations that we use here are dp by dt is equal to minus dou h by dou q, or minus dou h by dou r. Q represents our coordinates. And dr by dt is equal to dou h by dou p. Here p is our momentum. But here your momentum can be calculated as dou L by dou q dot. So it's nothing but mq dot, which we calculated in the previous instance. Or you can simply consider P is equal to mv, so it's nothing but mq dot. Now substituting this in our first equation, you will get dou by dou t of mq dot is equal to minus of dou h by dou q, which is nothing but minus of mg. Because if you derive this with respect to q, if you differentiate it with respect to q, then only this term depends. So then finally, plugging in all your values, you will get mq double dot plus dou m by dou t, because mass also varies. Because as a rocket travels, it expels gases with constant velocity and sometimes even ejects components. So mass varies, so dou m by dou t into q dot is equal to minus mg. Actually, if we verify, we see that we got the same equation using both Hamiltonian and Lagrangian, which is a proof that our equation is valid.